This video will show you how to do a one-way ANOVA, the actual procedure, using what we call an analysis of variance table. These tables are very useful. So let's go through some basics again. Recall that our test statistic for an ANOVA is equal to the mean squares of the treatment divided by the mean squares of the error. Keeping in mind, we talk about the treatment, we're talking about the variation among all the different populations that we have. And in the denominator, when we're talking about the error, we're talking about the variation within each population that we have. With an analysis of variance, we're looking to see if the means of those populations are the same or if there's differences among the means. The idea here is if the variation among the various populations is much greater than our denominator, which is the variation within each population, then our sample would provide us sufficient evidence to conclude that the null hypothesis, where the means are all equal, would be rejected in favor of the alternative, which is going to say, hey, there's a difference somewhere amongst these means. Your analysis of variance is not going to tell you where that difference is right now. Right now, it's just going to tell you that your data provides evidence there is a difference. In the last section of this chapter, we will look into how technology is going to show us where those differences do exist. So again, recapping, your MSTR, the mean square of the treatment, is equal to the treatment sum of squares divided by the degrees of freedom, which is k minus 1. And these formulas, please, you should have your formula sheet out in front of you and following them on there. And then the mean square of the error, which of course represents the variation within each population itself, is going to be the error sum of squares divided also by the degrees of freedom. In this case is n minus k. Okay. Now, let's take a look at our formula sheets one more time. I'm going to pop that on the screen here. So one of the things I had talked about in a previous video, and I want to point out again here, is we have two sets of formulas for our our treatment sum of squares and our error sum of squares. The computing formula uses individual data values. That can get incredibly tedious. The formulas here, you are welcome to use those formulas. I am not going to do them in any of the videos that I work out because I prefer always the defining formulas. The defining formulas use what we call the summary statistics for each population. So what I'll end up doing is I'll go ahead and find the summary stats for each population and then use this formula for SSTR and this one here for SSE. If you do choose to try the computing formulas, you are welcome to do so. You can definitely do one for SSTR. Notice there is no individual formula. For the error sum of squares, you have to take the total and then subtract it. The total minus the SSTR. Okay, but I'm going to end up using these formulas here. So now, to help organize, we have what we call our ANOVA table. Something you're going to see. So the ANOVA tables are in the PowerPoints you can take a look at, and also on a test you will always be given a blank ANOVA table. So here's what it looks like. Starts, the first column represents what we call the source. And that is from either the treatment, again, we're talking about variations among the populations themselves, or the error, which is variation that goes within each population. On your calculator, if you decide to, you play around with your graphing calculator, your treatment is also known as the factor. Okay, so they represent the same thing. The next column is where you'll fill in your degrees of freedom for each. And then we have the sum of the squares. So it's the treatment sum of squares would go here. That's your SSTR. And your error sum of squares are going to go here. That's your SSE. And the last column is where, whoops, sorry, it's not the last column. Then we need the mean square of each. So that's just taking your SSTR dividing by degrees of freedom and your SSE and dividing by degrees of freedom. And then of course your last column is your F statistic. And this is what's going to help us calculate, or not calculate, but what's going to help us determine whether to reject or not reject. So this is what an empty, there are totals as well. And the total simply is the treatment plus the error added together. And we only do totals for, I'm going to erase this and only bring it down to here. We only do totals for degrees of freedom and for the sum of squares. We don't do totals for the mean sum of squares. So again, this is what an empty one looks like. If I were to fill in formulas, the formulas would start to look like this. And these formulas you can get directly from your formula sheet. And we have n minus k. So this represents SSTR, and you would get that formula from your formula sheet. You're going to put SSE in here. So this one is MSTR, which of course is your SSTR divided by k minus 1. And MSE is SSE divided by n minus k. And your F test statistic divided by, okay? And if you open up your textbook, you open up the PowerPoint, you'll see some images of these tables. I'm going to go ahead and I'm going to move this up. And I'm going to give us a very small, basic set of data to work with. So I'm going to give you 3 samples. I'm just going to call them sample 1, sample 2, sample 3. And I'm going to put just a few numbers. These calculations can end up getting very tedious. I'll also create a video for those of you working in Math Lab for some of the larger problems on how to bring it into StatCrunch. So you'll get that information as well. So here we're given the actual data. Now, keep in mind, when I give you a test on this, I'm not going to give you the data values because then anybody can plug them into their calculator and get all the answers. What I'm going to end up giving you is what I call the summary stats. You will not have these data values. You will only have summary statistics. So what do summary stats look like? Well, that means just take the mean of the first sample. So the mean of sample 1 is a 6. Take the standard deviation of 8, 4, and 6. That's using the basic sample standard deviation formula from chapter 3. It is on your formula sheet. That's going to be a 2. And of course our sample size is a 3. For sample 2, my X bar is a 2. My standard deviation is a 1, and N2 is a 3. And again, you don't have to worry about calculating standard deviation on the test. I will give them to you. So for my third sample, my mean is a 4. My sample standard deviation for number 3 is 1.41, and the size of number 3 is 4. The last piece of information you always need is X bar. This X bar is the mean of all, in this case, 10 pieces of data. Since there's only 10, we can add them up and divide by 10. I showed you in one of the previous videos how to get a weighted average based on different sample sizes, so you can go back and check that out. But the mean for this one, this is the mean of 846,213,4363. It comes out to 40 divided by 4. So it is, I'm sorry, 40 divided by 10, not 4. So it's 4. So here's the data we're going to work with. Anytime you're doing an analysis of variance, your null hypothesis is always mu1 equals mu2 equals mu3. Your alternative, you have to write the sentence, all means are not equal. Is it not enough to go mu1 not equal mu2 not equal mu3, because that would be incorrect. You have to write they're all not equal. So now let's start our chart. You'll get used to doing these charts. So I have the treatment or factor, remember it's also cofactor, and the error. Whoops. I don't know what happened there. Hold on. Okay, we have degrees of freedom, the sum of the squares, mean sum of the squares, and our test statistic. All right, so let's start with degrees of freedom. Your degrees of freedom for the treatment is k minus 1. That's the degrees of freedom of the numerator. There are 3 samples, so it's 3 minus 1, and it's 2. Degrees of freedom for the error is n minus k. There is a total of 10 altogether, minus 3 populations, so that's going to be a 7. Now, for SSTR, that one you're going to have to work out on the side here. Okay, your formula for SSTR, take a look at your formula sheet. You want the defining formula. It's going to be each n, so I'm going to start with 3, times the sample mean, which in this case for number 1 is a 6, minus the total mean of 4 squared. So you can do that 3 times, 1 for each sample. So for the second one, we have a 3 again. But this time we have 2 minus 4 squared. And for the third one, we have a 4. And then I have what looks to be, sorry, 4 minus 4. Do the math, work that out, and you should get a 24. So 24, what goes in that location? The next one, I need SSE, the error sum of squares. Take a look at your formula sheet. Again, the defining formula. It's going to be each sample, you do n minus 1. So since my first sample size is a 3, it's going to be 2 times the standard deviation squared. For the second sample, which was also a size of 3, it's going to be 2 times that standard deviation squared. And for the third one, I have a size of 4, so that's going to be 3 times that standard deviation squared. And again, if you work that out correctly, you should get 16. For the mean, you're going to simply take 24 divided by 2. It's going to give you 12. 16 divided by 7 gives you about 2.286. And I'm going to run out of time on this particular video, so let's get that F test statistic, of course, is the 12 divided by 2.286 gives us 5.25. So now our test stat is 5.25. Let's do a quick critical value approach. Let's suppose I didn't define it yet, but let's do a 0.05. And let's take a look at we have 2 for the numerator and 7 for the denominator. So find 2 for the numerator